Hey everybody, welcome to the very last day of notes for the entire school year. I can't believe we've made it. Um, and I can't believe I'm giving my last lecture to no one. Because you guys aren't here and I miss you. But anywho, so we are going to be finishing up the notes today. We're going to be talking about this thing called entropy, which is pretty fun uh, to look at. So let's go ahead and get started with our very last day of notes ever. Unless you have me next year, then we'll have more notes. Okay. Alrighty, guys. So we're going to go ahead. We're on number 46. Now, 46 is up here, but also part of 47. So 47 says compare and contrast spontaneous and non-spontaneous reactions. Spontaneous reaction is on this slide, and then the next slide will have non-spontaneous. So we've got 46 and then half of 47. So we briefly talked about this before, but energy that is available to do work is called free energy. And I just realized a typo. That should say is, not in. So energy available to do work is called free energy. So that kind of makes sense, right? So energy, it's free, it can do stuff, it's not currently being used for any type of reaction, so it's free to do whatever kind of reaction is needed. Now there are two types of chemical reactions that we'll talk about. First are spontaneous reactions. So I think a lot of times when we think of spontaneous, we're like, oh, it's just so random and they just kind of do whatever they want. It's not quite exactly what's happening in chemistry when we talk about spontaneous reactions. So basically what a spontaneous reaction is it, well, it's a reaction that occurs naturally and it favors the formation of products at the right conditions. So basically it produces a lot of products, produces a lot. And it releases a lot of free energy. So it releases, makes a lot of product, lots of energy is being released. Now, one really great example of this are fireworks. Fireworks, you set them off and they create this huge explosion, right? And so that is actually an example of a spontaneous reaction. It produces a large amount of energy, or a large amount of products, and it also releases a lot of energy. So here, and I just pointed out my screen, obviously you can't see what I'm pointing at. Here we have this image. So spontaneous direction is downhill, proceeds unaided. So with spontaneous reactions, typically they don't take a lot of work. They don't need a lot of effort to cause the reaction to happen. So for example, rolling a ball down a hill. It rolls down pretty fast. All this energy is being released, but it didn't take a whole lot of effort to get it there. Now, non-spontaneous is the opposite. So this is the other half of 47. So a chemical reaction that does not favor the formation of products is called a non-spontaneous reaction. So this is a reaction that will produce, wow, I have so many typos. Such reactions produce, not produce little, if any, product. So it's like you put a lot of work into something and you don't get a lot in return. So these are like little tiny reactions that don't really do anything cool. So for example, with the spontaneous, we had the ball rolling down the hill. But for a non-spontaneous, it's kind of like if you have a ball, and you're a big heavy ball and you're trying to roll it up the hill. So you have to put all this work, all this effort into it, and you don't really get that much satisfaction, I guess, out of it at the end. So you put a lot of work into it, it just doesn't really do much. So that's the difference between spontaneous and non-spontaneous. So spontaneous releases a lot of energy, not very much effort to make it go off, while non-spontaneous takes a lot of energy, but it doesn't really give you much in return. So here we have a couple of examples. So 48 and 49 say to give examples. So here are a couple, and of course you guys can come up with your own. Earlier I did say that fireworks are a great example of a spontaneous reaction. Another one is rusting. So that's another one. Not a lot of energy, or not a lot of effort is needed to make rust, but when it does happen, it creates a lot of it and it releases a lot of energy. Same with melting ice. That is another type of spontaneous reaction. It doesn't take that much energy, and you get quite a bit in return. Now, for whatever reason, I don't know why you would ever want to do this, but if you were removing sugar from a cup of coffee, once again, I don't know why anyone would do that, but I've never worked at Starbucks, and so I don't know what weird things people like, but this would be a non-spontaneous process or a non-spontaneous reaction. It takes a lot of work, and all you get is a sugar-free coffee, which probably doesn't even taste very good. So it takes a lot of work, don't really get much back. So those are kind of some like real life examples of spontaneous versus non-spontaneous. So all of this leads into something called entropy, and entropy is fun. So this is 50 through 52. So entropy is the measure of disorder. So disorder meaning like how crazy something is. So basically, the law of disorder states that the natural tendency for a system is to move in the direction of increasing disorder. Kind of interesting because I feel like we think of nature wanting to be organized and things are nice and balanced, and they are, but typically they don't want to be in this very like rigid order, right? Things in nature would rather be able to do their own thing and be able to do what they want when they want. So we can see that in chemical reactions. We can see that behavior even in humans. I'm sure a lot of you guys are, you know, with your parents like, oh, stop giving me all these rules. I want to go do my own thing. You are literally obeying the law of disorder, which is what happens in nature. That's just what nature does. So it's just the measure of, so entropy is the measure of disorder, and typically what nature wants is to be disordered. Of course, still maintaining homeostasis, stability, things like that, but they want to be more random and have disorder. So reactions in which entropy increases as reactants form products tend to be favored. So reactions that tend to make something more disorderly is favored, which is kind of weird. Like when I first learned that, I thought it would be the opposite, but it's not. Things want to be disordered. And that's what entropy is measuring, is how disordered something is. So here is an example. So 53 says give a real world example. So here's an example. So here we have these dogs, and these dogs are on leashes. They're having a good time walking around, whatever. They're very low in entropy. They're very ordered. There's no craziness. But then we see this other picture here, and the dogs are going crazy, a huge increase in entropy. There's disorder, there's randomness, and those dogs are probably a lot happier just running around, right? And chemical reactions, nuclear reactions, they all behave the same exact way. They want to be able to run free like these dogs are. So this has a low entropy, and this has a high entropy. So high, the more disordered, that is more favored. So here we got a couple of images. So number 54 says, explain how each of the images below relate to entropy. So there are two images I'm going to show you. So we have solid, liquid, and gas. And even though, if you guys remember from chapter 17, it takes a lot of energy for a liquid to boil into a gas, it is still more favored than being kept in a liquid or in a solid form, because it wants to have that increased entropy, it wants to have that randomness. So as we change states here, we are increasing the entropy, and these guys are really happy. They are pretty stoked to be able to just bounce around however they want. Here we have a solid, and someone hit it with a hammer, and they broke it into a bajillion pieces. So they are increasing the entropy. They are increasing the randomness of the atoms in the structure, and things are just disordered. Here's another one. So this image here shows decomposition. So here we have two water molecules, and when you put electricity into water, it breaks apart into hydrogen and oxygen molecules. So when they were water molecules, they were nice and proper. They obeyed, or they, had low entropy. They were very structured. But as that electricity hit the particles, these hydrogen and oxygen molecules suddenly were able to move around more freely. They could be more random. And then, of course, we can see the same here with boiling water. As we increase entropy, the more random and more disorderly the particles inside of the water will get. All right, so we have number 55. So quick thing before we go into this. So entropy, if you remember, we literally just talked about it. Entropy is the measure of disorderness or the amount of randomness. And enthalpy, if you guys remember from chapter 17, that is the change in heat. So the size and direction of enthalpy changes and entropy changes. So basically what this is saying is the size and direction of heat changes and orderly, or the randomness changes together determine whether reaction is spontaneous. So what causes fireworks to be spontaneous while trying to remove sugar from coffee in that real world example is non-spontaneous? What is causing that? And it's just the amount of heat changes and the amount of, or enthalpy, and the amount of entropy changes or change of disorder. So if we look at this chart, it says enthalpy change. So as enthalpy decreases, so as it releases heat, and if at the same time the entropy increases, then the reaction becomes more spontaneous. So one example of that is decreasing, so putting out heat and increasing randomness. So for example, like boiling water, perhaps. That heat is being released on all that steam. The particles are moving around really crazy, and that releases a lot of energy. And so that would be a spontaneous reaction. Now, of course, if it depends on some other circumstances. So if we increase enthalpy, increase entropy, it will maybe be favorable, just depending on what exactly is changing. So it's kind of interesting to see how entropy and enthalpy work together to determine how a reaction is going to happen, how much is going to release, how much energy is needed. So we know that decreasing enthalpy, decreasing heat, increasing entropy will make the reaction spontaneous. But if we increase enthalpy, so if we take in heat, and if we decrease our entropy, then that reaction is not likely to be spontaneous. Okay, so let's take a look at, oh, nope, I guess I don't have that chart. The chart in your notes. Let's take a look at that chart. So these kind of images that we see here. So if we, I don't know why I didn't add this to the slide, but that's okay. So just looking at it, looking at the top part, it says heat release is favorable, entropy increasing is more favorable. So that will cause a reaction to become more spontaneous. So if you have a stronger favorable reaction happening, that reaction is more likely to become spontaneous. So if we look at all of these three on the top, these three here, all of them have, except for the first one, have one thing that's favorable and one thing that's unfavorable. But if that favorable, like the entropy increasing, if that arrow is larger than the heat absorbed, I'm looking at the second one, for example, then that would still make it a spontaneous reaction. So you got to look at the arrows, how they are moving, which one is giving more energy, which one is losing more energy. So with 56, it says, explain why spontaneous reaction can occur when one factor is unfavorable but not when both factors are unfavorable. So looking back at this chart, you could see that there's always one that at least says it's favorable. But if we look at this bottom one here, the very, very last one has two unfavorable. So heat absorbed, unfavorable, entropy decrease, unfavorable. So why, if we have one favorable, why are we still able to have a spontaneous reaction? Basically is what it's asking. So in short terms, as we have talked about, enthalpy and entropy determine how spontaneous a reaction is. So those two working together are very important for determining how spontaneous or non-spontaneous a reaction will be. So if both factors are unfavorable, the reaction is not spontaneous. So we could see, especially with this bottom one, or all of these, if the unfavorable one has the largest arrow, the reaction will be non-spontaneous. And I wish I could, so we could see here, where's my pencil? The heat release is favorable. Oh, sorry, let me look at this one. So we can see that this one here, the favorable one, has a longer arrow than the unfavorable one. And so that's why it's still a spontaneous reaction. But if we look down here, the unfavorable one has a longer arrow than the favorable one. So that would make the reaction non-spontaneous. So if one of the factors is favorable, it can offset the unfavorable factor. But of course, that goes the other way around. If one of the factors is unfavorable, it can offset the favorable reaction. All right, guys, that is it for this chapter and for this school year and for notes and everything. It's crazy. So anyway, just wanted to say that I've had a great time with you guys this year. I'm sad it had to end this way. I wish I could see you guys all the time and chat about nerdy chemistry stuff more often, but just wanted to say thank you guys for a great year, and I'll see you hopefully in the fall. All right, see you later.